only depends on the fusion rules. The adjoint subcategory is the subcategory, so it depends on the associativity you have. It's the same associativity that you have in the category. But what I meant is since this condition of stopping at some point in Beck, it only depends on the fusion rules, but not the adjoint subcategory is a subcategory, and we have same kind of associativity than the one that is in the category. The potency is what is only a authentic invariant. I was not very precise on that. Then there are a couple of things I wanted to say is the equivalentization. There are some generalizations of this idea that you take some algebra. Here I'm taking a nice algebra which is related to a group. It's the algebra functions over this group. But you can do this idea of taking modules over nice algebras and getting nice categories out of this also. So there are some notions of nice algebras and taking local modules, and you still get some cases. Or if you want modular categories, that's another way to do it. I will maybe mention local modules at some point, but I don't think I will go in details into that. Then other thing I wanted to mention is that there was a question about the possible other definitions of grading, and actually with gauging and all these things, people wanted to think on more general settings. So as I mentioned, I think Bishop has some ideas for hypergroups, but also John Switch and Han Wang, maybe some other people were thinking about Hoff monads to do this kind of stuff of gauging instead of just groups. So there has been other exploration and some others that have been thinking, but people wanted to try to think on these on more general settings too. And I made a list, and I deleted some of the things. I made a list that maybe later help us to compare. I wanted to remember to say these things. Yeah, to help us to compare. And for math question, I mean, if you want to think about all modular categories coming from a modularization, you will need to think that this is equivalentization of something, and then you need to see what are the possible categorical actions. So depending on your modular category that you are looking at, and you look at the tensor autoequivalence, maybe that are trivial and maybe or not, or maybe that are mixed or not a group, but you can always think that that's the trivial case using the trivial group as we said before. So if you want something more interesting, I don't know, it will depend on the tensor autoequivalence. Sometimes you may not find something very new. So now I wanted to continue on this kind of extension flavor thing, but I will present a construction that it's less general than extension theory, but it's very computational nice. You can compute most of the things that you want out of it. So this is called Zesting, and that's going to be useful in math and physics. So this construction we started developing a long time ago, like 12 years ago or something, when we were looking at a very explicit problem. We want to classify modular categories of dimension 36. So that's why classification is useful sometimes. So we found some nice family of fusion rules that were similar to some quantum groups fusion rules, but not exactly the same. We were a little bit twisted. And we wanted to know if there was a realization for that modular category. So if there was, or for that fusion rings, if there was a modular category with that fusion rule. And we did construct one in a very ad hoc way. Later, a couple of years later, we were thinking about this problem of minimal modular extension. So like 16-fold way of Kitaev, if you have supervec, there are 16 ways to embed it in a modular category. 8 of them are Ising, 8 of them are pointed. And this could be extended. If you have a supermodular category, so the viewer center is supervec, we wanted to know if there are exactly 16 ways, and the answer is yes, and it was proven steps. So first, Lan, Kong, and Wen proved that there can be certain extensions. David Reuter and Theo Johnson-Frey proved that there are actually 16. So it's a very interesting work. And we were also working on that, and what we could prove is that these 16 things will come in families of 8 and 8. And each of them will be related by this construction setting that was similar idea to the one that we did in the 16-fold way. But again, this was kind of ad hoc in this super modular case and that. So a couple of years after that, we did a more systematic approach to Zesting with some of my collaborators, Colin Delany, Cesar Galindo, Eric Rowell, and Ching Sang. And it fits in this program of extension theory. So Zesting is a particular case of extension theory. So again, it's not the more general case. Maybe let me say this. It's a particular case of extension theory, setting of Nikchik and Ostrich. But let me tell you what are the advantages, and let me explain the construction, because we don't define it exactly doing extension theory per se, but then you can see that it's naturally an extension. So I will start with something that you can do this for fusion categories, you can do it for braided fusion categories, you can do it for pivotal braided fusion categories. I will do it for the middle one, braided fusion categories. And then out of it, you will get a new braided fusion category if certain obstructions vanish, because as I'm telling you, this is an extension theory, so there will be some obstructions. So what we wanted to do, we wanted to deform or like twist the category a little bit. We wanted to change the fusion rules a little bit, and the associative a little bit, and the braid a little bit. And I will basically only mention probably the associativity and the tensor product, but the braid is similar. But what is the setup for this? I will start with a graded category. So I will decompose my category in this way that I mentioned a lot of time. In this time, I'm not saying that it's an extension, but you can think it's an extension of the trivial component. So I'm just doing before, because we will use this grading for things. And I will start with something that is strict, meaning that associativity is the identity, just to make it easier to define the next one. You could define it without this, but it's a little easier. So what I will do is I will pick an object X. So okay, so this C tilde is equal to my category C as abelian categories. So what I'm saying is I have all the same simple objects, the same direct sums and all that. What I will change is the tensor product, the associativity, and all that part, the monoidal and the braided structure. So I will pick something that is in the G component and something that is in the H component. And I want to define how I will tensor. And as I told you, I don't want to do anything very dramatic. I will use the old tensor product. And here I will not write parentheses because I don't need, I assume strict. But I will deform a little bit this. How? By something that only depends on the grading components of the object, not the objects themselves. But for this not to be very drastic, I will ask for some conditions. So this will be an invertible object, something in this GC. So an invertible object in the category. But moreover, I don't want this to be in any component. I want this to be in the trivial component of my category. So it will be an invertible, one of these dimension 1 objects, but that lives in CE. So if you see, I started with something that lives in CG, CH, and I tensor by something in CE. So this is still in the same component as my original tensor product. I didn't change the grading. Okay? That's one thing. Okay. So now, I want to know a little bit more about this lambda function. So, in principle, because I want a fusion category, I will want some associativity. I will be sadly pessimistic, and I will read from top to bottom today. And let's try to see how this should be if we are having something associative. I'm not sure if I'm using nice letters, to be honest, but okay. I want to define my new associativity, so I will see how these objects are, and I will be using some graphical calculus to do this, okay? So this first part is just xg. Now, okay, maybe I will keep the tensors. YH and the lambda. But now I need to tensor with this object and with the lambda that has in the last component k, which is the grading of this, and in this one the grading of this object, which is GH. Oh, GH. Yes. So I make a mistake with the labels, tell me, because I might. So now I want CG. Here this will live again in CHK. So I will tensor by lambda GHK. But now I need to tensor by this object in my old category. So this is a YH ZK lambda HK. Right? And what I will do is I will do as less as I can. So things here I could do just identities. I don't need to match. What I will do is I will move my object here. And for this I will use the braid of the category. So I'm using the braid here of the category. To be totally honest, in one paper we use the braid, another the inverse. There are some choices here. Let's use the braid. And here I will need to have some, I want this to be an isomorphism. I will have some isomorphism between this product of invertibles and this product of invertibles. So this isomorphism, which I'm writing here, there are a couple of things that we can say, but this isomorphism is nice because it's telling me something about my lambda. So this is an isomorphism between this, and this will induce, so I have this isomorphism. If I think, I mean, maybe here, to be more precise, I should have written invertibles, because I'm doing tensor products. But this will induce, if I take isomorphism classes of this invertible, this will induce a 2-cos cycle, because this is a 2-cos cycle condition. So this is inducing a 2-cos cycle condition on the group of invertibles of the single component. So this lambda basically is inducing lambda tilde, but usually we use the same notation, a 2-cos cycle from GC, which is the group of CGE, the group of invertibles in the trivial component, to the field. And actually this map here, because these are invertible, the product of invertibles is invertible again, remember that this is a group. So basically this will be some multiple of the identity that we have. So it will be a number. A lot of the time we will take that scalars out. So why we have, I told you this is extension theory because if you see, I didn't change the grading. I'm telling you who is the tensor product, I'm telling you the potential associativity. For this to be really an associativity, I need a pentagon. That pentagon is the one that gives obstructions. So pentagon gives some homological obstructions that I will not write. But it's not surprising because there should be homological obstructions coming from extension theory, right? It's the one that I wrote 04, I think I wrote it. That's the homological obstruction, which is again associativity, because the 03 is for free if you started with a categorical action in that step. If I have that is the one giving me the fusion rules, basically. So that one is fine. So I will not do the part of the braid, but if you start with a braided category, okay, maybe let me say some comments. Here, you can tell me, but you're kind of cheating because if you start with a fusion category, you don't have this here. But instead of taking these to be in the invertibles of the center, or the invertibles of the trivial component, we take them to be in the being invertibles that have a half braiding with things with the other objects. So it's a relative center. It's an object in some relative center. So we take a more restrictive thing, but we can do it in the fusion case also. If it's braided, it's easier because we have the braid and we choose that. We choose any invertible in the trivial component. Otherwise, we need to restrict to some special kind of invertibles in the trivial component. But we can do it. And again, for doing the braid, we do something very mild. We change the braid a little bit by some, in some way, but I will maybe not go into the braid just for things. But also in the braid will be some obstructions. Usually this braid Zesting gives actually some character, some by-character of the group going on, but I don't want to talk about that, and it's related to this braided extension theory that I mentioned that Davidov and Nikshik developed. But maybe that's fine. But maybe let me tell you why Zesting is interesting. I told you some things that happen with Zesting, but there are some nice consequences that are more or less easy to see. The rank, because I didn't change anything in the abelian structure, is unchanged. We can also prove that the dimensions of the objects, the Frobenius-Perron dimensions of the objects, are unchanged. Maybe here I will put in C and C tilde, it's the same. So Frobenius-Perron dimensions are preserved. We have, of course, very specific, explicit, maybe it's a better word, explicit fusion rules and associativity because I'm giving it to you. And why this is useful? Zesting was very useful because at some point people wanted to, for example, categorize certain fusion rings. Valcourt, Wren, and Liu found certain fusion rules and they didn't know if they came from fusion categories or not. They passed all the tests that they needed to pass, but they still couldn't construct it. And using Zesting, they were able to construct it. Or the same happened to us with the Frobenius-Perron dimension equal to 36K. So that helps for categorification. But also, we can compute in the braided case. We have an explicit formula for the Mueller center of the new category. Why that's nice? Because actually Zesting can change the braid dramatically. You can go from symmetric to modular sometimes, or not degenerate if you want. So you can change, you can also change the pivotal structure, but I will not even mention that. But you can go from symmetric to non-degenerate. And there are some pointed examples which shows this. So we computed the Mueller center, and there are some cases in which we have a lot of control, and we know that we go from modular to modular. So it's another construction to get modular. And in these cases that you start with modular and you end with modular, so if C modular and C tilde modular, which we have some control on this. Then for this we have explicit formula for S and T tilde. So for the modular data of the new category in terms of the modular data of the original category and the lambda nu and other things that you need to define the new modular category. There is a new thing for the braid, which is called T, and a new thing for the pivotal structure, which is called F. So in terms of that, we have that. Also related to these modular isotopes that I mentioned yesterday, we have these examples from Mignard and Schauenburg, which were representations of twisted doubles of very specific semi-direct products of set Q and set P for P dividing Q minus 1. In that case, we wanted to understand better why this phenomenon happened and how we could explain it. And with Colin Delany and Sang Kim, who's here, so we look at how Zesting changes links and not associated to the category. So as I was saying, maybe here I should add that we don't change, or we know how explicit formula for braid group representations, which is useful because there are some conjectures about the finiteness of this, the image of the braid group, and we have control over that. We know that it preserves it. But now we also have formulas, and these formulas are very nice because basically we can split and we can get the same Lie and not invariant modified by some factor that depends only on the Zesting data. Okay? Basically on this part and the lambda, nu, and all that. And it was helpful to clarify what happens. So basically some explicit formulas for L tilde, if you want. And then actually Colin has some follow-up work on this, which is almost finished and coming up. So it's interesting. And again, after we had this, for example, Izumi and Grossman, they computed center of quadratic cut. You have a question? No. You can.
I was just going to ask, do you also have an explicit formula for the like supermodular data after Zesting?
No, we didn't do the supermodular because also the S antimatrix are a little bit. You need to be careful when you define the S antimatrix are defined as the same, and we didn't look at it, but probably you can do it. I mean, in the fermionic paper, we did look a little bit into that, but I don't remember if we write explicit formulas or only for cases that we were looking at PSU2 level for M+2 or things like this. I don't remember because it's an old time, but we did that case explicitly to see how the easing and the point and all that changes. But I don't remember if we wrote the restrictive, the kind of super S and super T, because there are some ambiguity in that case, so you need to be careful. But I don't remember if we have explicit, but probably you can do it because it's very explicit construction.
If you have the formula, do you know of a good way to describe how the congruent subgroups change?
We didn't check, but that's interesting. That could be good to check how the congruent subgroup change, because it will need to, you need to look at the order of the T matrix, so it cannot change that dramatically. The congruent subgroup will be given by the order of the T matrix, and we have this T matrix in order of the all T matrix and some of the other invariants coming from here. So it will be computable. And actually that's how we prove the property F is preserved here. We also use the T matrix a little bit. So you could, I mean, we didn't compute that.
For braid groups.
Yeah, but we didn't compute the congruence, but you can compute it from there by looking at the order of the new T matrix. So it can be done within graphic, but yeah. Yeah, I was saying that Grossman and Izumi at some point, they found possible S antimatrix coming from some centers of quadratic things, but they didn't, I mean, they wanted categorification of possible modular data. And Bonderson, Rowell, and Sang, and Wang, sorry, they gave realizations of some of the examples using Zesting and using gauging. So that's why it's also useful for categorification, because a lot of the time we don't know if they can be or not categorified. But maybe let me say something else. So something that, so this is good, but maybe a comment, a remark. Central charge can change, and with class. I mean, these two are related. So. And in particular, I was telling you that the 8 easing are related by Zesting. And the 8 easing have different central charge. When we prove this thing that the 16-fold, we have 8 and 8 families. If there exists, it has 8 and 8. 8 of them were related by Zesting, other 8 were related by Zesting. They have different ranks, they couldn't be really related by Zesting between them, but this family were, and the 8 easing have different central charge. So in this case, the central charge could change. So we wanted to understand a little better this phenomenon. We also wanted to hopefully have a more physical interpretation of this. So for that, we started studying a different construction that is called the condensed fiber product. And it's related to other constructions in, I'm not, maybe I don't want to say this that much because I'm not an expert on this part, but I'm not an expert on the physics literature, but it's related to some construction, again, by Lam, Hong, and Wen, that I mentioned before, by certain constructions of Davidov, Nishik, and Ostrich that is related to the group. Constructions by Sang, Vish, Banat, and Wen, and constructions by Singh, Lam, and Cyber. There is this hierarchy construction by Wen that is related to this condensed fiber product that I will mention, but kind of the idea is that we want to stack two theoretical layers and do some kind of condensation. That's supposedly in physics work, but I don't know, maybe don't quote me in that way, but that's kind of the idea. So we will define a mathematical construction for that, and that's the one that I was saying that I might involve some local modules. Maybe let me tell you one more thing. So we did all this first in this general, so we call it associative, braided, and pivotal Zesting. But then other very useful kind of categories are these G-cross categories. So we wanted to know how, or if we could do Zesting in the G-cross setting, how, and we were able to do also that. So what we did in the G-cross setting, if we started with a G-cross category, instead of just a graded category, G-cross, so in that case I wouldn't have this, but I will have the action and the cross braiding, right? So what we did, we adjusted in the same way that I'm saying here, basically, the fusion rules and the associativity. There is some details that you need to have in mind, because here when you do some of these things, some actions will appear, so you need to be a little bit careful. But we deformed that, and we proved that if you started with a G-cross category, and you do this adjustment of the associativity, like this testing, the result is again G-crossed. And for that, we use this result that I mentioned before, that G-crossed categories are the same as certain central extensions. Doesn't matter, but it's, for now, take it as a black box, but basically let you encode the braiding and the action together, and that's how we got it. Okay? So the next thing that I will use might or might not use it, depending how I'm doing on time. But I will mention the condensed product in a, I'm trying to see what to delete, in a, maybe in not the most general setting. There is a more general setting, but I might only present it in this setting. If we have time, I mention a little bit the more general setting. So let me tell you the setup for this condensed fiber product. And this is again the results that I will mention here. And this is very hard for me to, I don't know if I will be able, this symbol I don't feel very comfortable with. We will try. This is again with Colleen, Cesar, Eric, and Ching. So the same people that we did the Zesting papers. We wanted to kind of give this more, or this relation with this idea of condensing some stack theories, and we look at this. So let me tell you the setup of this. What I want to do is I want to start with some non-degenerate category. If you feel more comfortable with modular, think that it's modular. I'm saying this because it's easier. With some subcategory inside. So I will tell you who is this V set. What I want this V set to be, and I will explain how it will look after that, it's a pointed. So remember that pointed is basically vec AQ, because this is graded. So it's some A-graded vector spaces with some some quadratic form around giving you the braid. But I want this not to be any pointed. I want this to be symmetric, actually. So we will describe, because we know how pointed categories look and how symmetric categories look. So I will tell you how any of these B set will need to look. So any symmetric pointed fusion category looks like how I will describe it. So this will be back the Q set. Sorry that I changed the notation. And here I want to use B hat. So the characters of some group. Okay. For D, some finite abelian group. This set here, that it's here, is, because remember, we are in symmetric, so we want some central element of order 2. So this will be some central element of order minus 2, I should say. These are the characters of that group, and this Q set will be my quadratic form. Okay? So how I will define the quadratic form? This, as you see, depends on the set. That's where this central element plays a role. I will evaluate it in a character of this, and this will be just the value of this character at my central element. And this is always actually plus or minus 1. Because this is the central element of order 2. And any pointed symmetric fusion category looks like this. So we will use one like this. Okay? It's kind of reconciling that. I mean, it's a pointed braided category, so I want a abelian group, a quadratic form, but I want this to be symmetric, so the form needs to look nice. Okay? So the square of the braided commutes. So after I have this set up, for free, I will have some things on my category. So this is the setup. What this buys me, having this symmetric category inside my category, tells me that C is B graded. Who is B? My group that helped me define the symmetric category. Okay? So I will tell you who is the component, or how the component looks. So the component labeled by B in B will be given by all, the category generated by all the X in C, such that the square of the braiding commutes almost. Instead of commuting, if I put here one of these characters here, this will projectively commute. So it will be the identity up to a multiple, and which multiple? Via T. And I want this for any character B. And you can check that this is a grading. I will not go into that, but that gives me a grading, which is a little not right. So now we have this nice grading. It's a faithful grading. And something else that happened, that it's good, is that this set, my symmetric pointed category, lives inside the trivial component of the category, and something that I didn't define but I will mention, which is called the centralizer of the category, the trivial component. This is a symmetric thing, so it makes sense that the symmetric thing lives inside this. What is the centralizer? When I define the Muger center is the centralizer of the whole category. So now I will do the same. Are all the elements in C such that the square of the braiding of the element commutes with anything in the trivial component. So are the elements in C that are transparent with respect to the trivial component. That's what I'm picking. Okay. I'm saying commutes because since it's a braided category, this part, it doesn't make sense to ask if the product is commutative. It's commutative for everyone. So that's kind of the new abelian or commutativity thing that we are looking, the square of the braiding. What things are transparent? So these are all the things in C that are transparent with this component. Okay? And my pointed category lives inside that. It's a technical thing because that will help me to do that. So these are the kind of categories that I want. Now what I will do is I will take two of these categories. In the sense of the first setup, I will take C and D, both to be non-degenerate fusion categories with this B set inside. So C and D are both non-degenerate fusion categories such that B set lives inside both of them. So what we will do is we will define a product between these categories, as you might have noticed when I put the name, which has this weird symbol. Okay, let's see if I can do it. No, okay, it didn't work, but it's okay. You imagine how it looks. Maybe here is a B, it's a B of the group, D. And how we define this? So bear with me, but so one definition, if you know what are local modules, is I will define it using local modules. So I will do the linear product of these two categories that I started with, and I will consider the local modules with respect to the algebra of functions. Maybe let me write it as I was writing it before, KB. How can I do that? That's a question. In principle, you can ask me, but why? Because for doing that, what I need to do it was to have rep G inside or something like that. And happens that we have a copy of rep G inside, which we call in this way. And how we do it, we look at phi inverse that will live inside this thing. Why? Because B set lives inside both components. So it's not the diagonal thing, but it's almost. It's the thing and the inverse. And this ends up being equivalent to rep B. Other way to define this, which maybe, it's same or less insightful, I don't know, is taking this fiber product. What is the fiber product? That's a good question, and then I will dequadratize by B. So let me say what is the fiber product. If you have two graded categories, one thing that you could do, and there is a paper by Nikchik that includes this, is you can define a new graded category by the same group that you do just the linear product of the big components of each category. So we do that, and inside that you can also check that you have a B and you dequarantize by B. So this will be the condensed fiber product. It's condensed because you have the fiber product, and then we will dequarantize by B. I feel stressed about saying condensed because I know that it has different meanings for different people, but let's leave it there. And let me tell you some nice properties of the condensed product. Maybe I will write it here if I can. So some nice things about the condensed product. This condensed product. So I started with two non-degenerate fusion categories. I would like to know if it's braided, if it's non-degenerate, or what. This is again non-degenerate. And this is because when you take local modules, you get non-degenerate, basically. So in nice algebra, you take and you get a non-degenerate braided fusion category. So that's good. And actually, we have the dimension of this. It's the product of the dimensions of the two categories, C and D. Maybe this is what. So what's the dimension of these? It's the dimension of the two categories. But now I need to arrange, and instead of, as usual, getting more things, I will make the dimension smaller because I have the linear product, but I condense some things. So in this case, I will have the order of the group squared, but dividing instead of multiplying like we did in gauging. Remember, this is the opposite. It's smaller. And some things are good. I mean, I should say more things, but maybe some of them are not that meaningful. One other thing is, okay, we started with these categories that, for example, have this property. The condensed fiber product will also have this property. B set will live in the trivial component of this intersected with the centralizer. So it gets all these same things. So actually what we are saying is that we could get a monoidal category in which the objects are things like what I started with, non-degenerate braided fusion categories with B set inside. And this condensed fiber product will be a monoidal structure for that categories. Okay, I will not do that, but that's the idea. So the properties were preserved, non-degeneracy and B set being inside. But the one thing that I wanted to mention is because I told you, oh, for Zesting we don't know the central charge, how the central charge behaves. For this one we know. The central charge is the product of the central charges. So central charge of condensed product or condensed fiber product is product of central charge. And I will not write this because we don't have time. But you know that we have these easing categories. We have 8 of them, each with different central charge. If we take 2 of the easing categories, we can do the condensed fiber product by set 2. And what we get is one of the pointed categories that you have in the minimal modular extension. You know that you have 8 easing, 8 pointed. So our pointed categories of modular pointed categories of dimension 4. And what we get is, if you take 2 easings, we get one of the pointed, and that's how kind of explain how the central charges and things are connecting. And maybe something else that I wanted to say about the condensed fiber product before maybe moving into that. Okay, I will write it here. I was telling you, okay, I can get this monoidal category using the, can I say this, and then the condensed product, but you could tell me, okay, if it's a monoidal category, I need to have a unit for that monoidal. So I will tell you who is the unit, actually. And there is a natural category to look at, because I want a non-degenerate category that has B set inside. And I told you, if B set, if I have a braided category, a modular category, or a non-degenerate category that has it inside is the center. So I will take the center of this. This is non-degenerate. And because this is braided, this lives inside. In general, it wouldn't, but this is braided. And if you do C, I don't know why we picked this symbol. It's horrible, but it's okay. B, D, this will be C again. So this will be the unit for my condensed fiber product. You wanted to ask?
Yeah, I was going to ask, does one of these easing categories generate all 16 under the condensed fiber product?
Probably yes. I should think about it, but probably yes. I mean, I haven't think about that, but I think so because you can iterate and start moving between them. But I should think because how they behave, because you know in this pointed you have set 4 and set 2 times set 2 fusion rules. And which one you get changes depending on the central charge. If you start with an easing with central charge odd, not odd, but it will be e to the mu pi I over 8, the central charge. And the mu is odd. Then when you add 2 of them and it's congruent to 2, you get pointed with set 4, and if you get 0 mod 4, you get I need to think if you could get everything. I guess yes, but I should think about I don't want to, I'm not sure, I didn't check it, but it's a good thing to check. So as I was saying, we get we get a monoidal category out of it. But why I'm telling you about this, in part because it's a construction that tells you how the central charge behaves, but I also wanted to relate it with Zesting. And we have a theorem, I don't know what to delete, but I will delete something, so let's delete this part. So one of the theorems that we have, and let me say that we also define this condensed product in a more general setting. Instead of starting with a non-degenerate category, we started with a G-crossed category, and we did something similar, and we get a G-cross category. So we also got a monoidal category in that setting. But, okay, I will delete the setup, this part, the G grading that you get, and I will write the theorem here. So the theorem that we prove in this paper thing is, so if I have, maybe let me think. If I want to have one of these D non-degenerate braided fusion categories with B set inside, so one of the ones of the setup, right? But I ask that this category D is pointed. Okay, so I'm asking more. And I will ask a little bit more, bear with me. And if D has the correct dimension, which dimension? The order of B squared. Why? Because I want to relate it with the unit of my monoidal structure, the center of B set. The center of B set has dimension the order of B squared because it's the dimension of B set square. And I told you that dimensions under Zesting don't change, so that's what I want to do. Then in this setting, my category D is a Zesting of the monoidal unit of this monoidal category. So I will write like this just because I use this notation for Zesting. But what I mean is that there exists lambda, nu, t, all the data that I need to change it. So we kind of control, so all the Zestings, so the Zestings of this center give me all pointed categories of the correct dimensions that are non-degenerate and have B. And moreover, if, okay, maybe a B Zesting of some, maybe C tilde, but I didn't say, for C, again, one of these non-degenerate with B set inside, can be obtained, or may be obtained, there are some things I need to check, using the fiber thing. Let me see. As one of these fiber products. I have so much. Okay. D. For D, a Zesting of this B set. And here I'm being very imprecise because I wrote the tilde for Zesting, but the data for this Zesting and this Zesting is the same, with the same Zesting data. So maybe another way to say it is, if I have a C that satisfies non-degeneracy and has the B set inside, I can get Zestings of C using this condensed product and the Zesting of the center. Okay? But there might be other Zestings that I'm not sure if I can get in this way. So some Zestings can be getting. And there is a similar result for G-crossed. I will not say much more about this. I wanted to mention just a couple more constructions. So I will just mention them, and then I want to just close with some comments about the different constructions, but I will not go in depth but in the other constructions, because I will not have time. And there are probably more constructions that I'm not mentioning. But as you saw, so there is the equivalentization, there's also local modules. Sometimes we call one construction de-gauging, that you de-equivalentize and take the trivial component, and that's again modular, so we have other things. But there is this generalized orbifold that was first introduced by Froelich, Schweiger, and Runkel in two-dimensional conformal field theory setting, but then it was also formulated for topological field theories by different authors. In different series of papers with different things, but it was formulated by Kervil, Runkel, and Schaumann. And there are more papers that you can look, and they are interesting. There are papers by Kervil, Muller-Vicius, Runkel, Schaumann, and Schell that are also important in here. I won't be able to talk about this much, but the idea is that you have an orbifold data. And depending on the case, C will have different adjectives. In some more general setting, you have some kind of idempotent, complete additive ribbon category, but sometimes you can go to the modular setting and work there, depending what is your interest. And so this orbifold datum basically, has a lot of conditions, but so you need to have a suitable algebra object in C. So it's because you need some Frobenius structure and things, but I don't want to give the details, given that we have only 5 minutes. And then you need to have some bimodule in C, and a lot of additional maps, satisfying a lot of additional conditions, which we will not write, so plus a lot of conditions. But this construction is very nice because it unifies a lot of constructions that I mentioned before. So some of the conditions, I didn't say this, but some of the conditions that T satisfies lets you define a tensor product in a category that is of interest. Here I have an algebra. So one category that is of interest is we can look at A modules in C. And because of the conditions of T, we can define the tensor product. So, using this datum, we construct a new ribbon category using this datum. I will not enter in detail, but I wanted to say that recovers the local modules in some settings. It recovers the Drinfeld center in some settings. And it was conjectured that it also, if you started with something G cross, and if you have something G cross, you can do the equivalentization. So on one side we have that. So this orbifold datum again, you can construct the orbifold datum using the G cross in the trivial component, and you can recover this equivalentization using the orbifold. And that is work that we posted last week with Sebastian Heinrich, in Runkel and Abigail Watkins, that it's also here, but it's also, at the same time, there was work of Kervil and Hack that it was also posted. So this one has more a perspective on gaugings also. This one is more a perspective maybe on equivalentization directly. So this is also other constructions that we cover. So it's a unified construction, and I think there are more things that could be probably recovered that way. Other construction I wanted to mention very quickly, it's in groups. There is a notion of exact factorizations of groups, which basically, if you have, is this idea of all from U. So if you have the direct product of groups, it's one new group, right, for the semi-direct product. But the other thing that you can think is, okay, if I have two groups, I could think of the set given by the Cartesian product. What are the product structures that I can put on that? And that's basically the notion of exact factorization. There are other ways to define it. And there is a complete solution for that in terms of matched pair of groups and bicross product of groups. So there is a new group that you can construct that it's like a double semi-direct product. Let's say it in this way. So there is a similar question that you could ask. You could say, okay, what if I just take the linear product as the abelian category that I will look at? What are the monoidal structures? What are the associativity constraints that I can put on them, right? The tensor product and associative constraint. And that's the notion of exact factorization that was introduced by Jelaki. And there is a factorization. So Jelaki studied this. Also, Sonia Natale has some papers on this. Basak, Jelaki has more papers on this. And related to this, last year with Monique Mueller and Hector Peña-Polastri, we constructed matched pairs of fusion rings and fusion categories, and we also constructed bicross products, fusion rings and fusion categories. Actually, this notion of matched pair gives you all the possible fusion rings of an exact factorization, but we don't think that gives you all the possible associativities. It's kind of restricted. And again, by using extension theory, we can use this. So these matched pairs and bicross product was done for groups and for Hopf algebras. And we were curious what was the problem, why it was not done before for fusion categories, because there is a couple of years between these things. And we think that the main thing is that you can prove at some point when you have this that the gradients in the category can control what can happen. So at the end you can go one level down to look at groups and find the things in that way. One thing is that this is for fusion categories. If your category is braided, all the exact factorizations look like the linear product, and maybe the gradient is not exactly the tensor product, it's projectively that. But for G-cross, for example, we are thinking with one student how they will look. So maybe just let me close, I know I'm on time. I just wanted to say this is a sampler of constructions. So for this one, we basically know most of the things that you would like to know because it's just a direct product. For this one, we have some control of Frobenius-Perron dimensions. It gives you something modular for free, but we don't have control of other things, rank, for example, among other things. But it's one, if this category is graded, there is a very nice paper by Jelaki, Naidu, and Nikshik on how they recover this center using relative centers and equivalentization. So there are some nice papers on this, and they check when it's group theoretical or things like this, when this is graded by a group G, something like this. But there is still a lot of things to know. Equivariantization is nice. There are papers about, we know the dimension and we know how the fusion rules work, this paper by Boursion and Natale. The equivariantization, I feel like it's a little bit more complicated. We know the dimension, but we don't know the fusion rules always, and would be very nice to understand better. In some cases, when the group is cyclic or things like this, we know more, but not always. Extension theory is very powerful, but sometimes it's hard to really compute the extension, the possible extensions, but it's powerful. Even for extension theory, it's very useful to be able to compute Brouwer-Picard groups or the groups of braided autoequivalence or of tensor autoequivalence of things. Gauging, again, it's also nice. It gives you central charge with class, but there are obstructions, and we don't know fusion rules, S antimatrix, braid group representation, all that things are open and would be nice to know. Zesting, we have control on many things which I just deleted, but fusion rules, S antimatrix, Muger center, braid group representation, links are not equivariance. We have now more of an idea on the central charge because of this connection with the condensed product, but we don't know all of that thing, so it could be interesting. And it could be also interesting to know if we can generalize in some way, as there were questions today, extension, gauging, or Zesting. Instead of having a group, what else we could have. And for this kind of thing, we would like to know if these are all the possible exact factorizations, if we could have more. We are computing modules over these things because it's always interesting to be able to do extensions and to understand Morita classes. So these are some of the things we are working on. maybe let me say that I promised to say something about fusion two categories. I will not because I'm finishing, but I will say something. The idea is that you should take away that classifying, constructing modular categories is hard. We are putting a lot of effort on that. Fusion two categories are also hard, but we do have a classification result for fusion two categories. And yesterday I was talking to you and I was introducing this group theoretical or weakly group theoretical. Group theoretical basically was that we could describe the group theoretical and fusion categories that you could describe using cohomology and groups, basically, and some operations. So a natural question is, can we also do something similar for fusion two categories? Describe them in terms of lower categorical data. This is very rough, so take it not precisely. So what would be lower categorical data? Would be braided fusion categories, but understanding everything that we want about braided fusion one categories, like with classes, Raoul-Picard group, everything that we want, plus groups and cohomology and these kind of things. And in that case, the classification tells you that you can do that. That for fusion two categories, we can describe it in terms of lower categorical data. Again, I'm not being precise. Sorry, I went over time, and thank you for listening.